Hello everybody, welcome to our first video lecture of Discrete Systems course. In this course, I will review our fundamental knowledge of signals and systems. Okay, so let's start with the signals. Okay, signals. So we have two types of signals that we will cover in this course, continuous time and discrete time. And they're very critical for, both of them are very critical for our system. So what's a continuous time signal? Is technically a mapping from real numbers to the real numbers. So let's F is a signal. It's a mapping from R to R. This is a bilateral signal, okay? And in a unilateral case, it's a mapping from R plus to R. Again, so the examples are very simple. F of t is equal to sine of t, f of t is equal to exponential of t, or f of t is equal to the unit step function. Okay, so these are some example signals. Okay, so graphically, a signal looks like this. Okay, so let's assume that. Okay, that's fine. Okay, so this is unit step as we already know. Okay, or it can be like this or anything like this. As you can see, continuous time signals can be discontinuous. The time is continuous, but the signal itself can be discontinuous, as in the unit step or impulse function case. Okay, so in a discrete time signal, it's also a mapping, but now mapping is defined from z to z, so it's technically integers to integers. Okay, this is unilateral case. Or in the bilateral case, it's a mapping from z plus to z, bilateral. Okay, so if I want to show a discrete time signal, we use a slightly different graphical terminology. Okay, this is like this. Okay, let's change the color again, and let's change the topic. Okay, so we show it like this, right? Okay. In discrete time case, now the time is discrete. Of course, the signals is also discrete. This is 0, 1, 2, 3, 4, 5. These are indices. This can be a sampling of the real time, or it can be other sequence that depends on an artificial concept. Okay, good. So these are the signals. And now we talk about systems. Okay, so what's a system? System is a mapping from a set of input signals to the set of output signals. Okay. So how we show systems in general, we really like to show them using block diagrams. Do you remember? Okay. So let's assume that this is a continuous time system. That's S of C. Input is U of t and output is Y of t. In a discrete time system, SD, input is U of n, output is Y of n. Okay. So a mapping from set of input signals to set of output signals. Same for continuous and discrete time. Okay, the definition are the same. Of course, the system properties are different. Okay, so mathematically, we show a system as like this. Okay, Y of t is equal to SC UT. Okay, or in the discrete case, Y of n is equal to SD UM. Okay. So instead of this, if I write like this, okay, this is, okay, so let's clean them. So for that, okay, this is good. Oh, nice, like that. Okay, so if I write this, f of u of t, this is different. Okay, this is a function where output depends on u of t. U at this, allocate this t. So this can be a system, but this is a specific system that we will cover later. In general, we need to show the system definition using a different concept, and this is how we define in this course and in many linear system theory courses. Okay, so technically, the mapping is operated for all u, and sometimes we show it like this. Instead of just writing t, our S of C is technically applied for all u, and that kind of means that we are just taking into account all of the time. In discrete time, the S of t is acting for all u. Okay, the input is all of the inputs, and output can depend on input at any time. And this will give the dependence, a dynamical dependence to previous or future inputs. Okay, now we started to talk about the properties of the system. Let's do it in the next slide. Okay, good. So, properties, linearity. Okay, so when a system is linear. Okay, so before going into the mathematics, just write this. Okay, we have inputs and outputs. Okay, we already know that our output can depend on previous and future inputs because it's the feature of dynamical systems. But the basic idea is we do an experiment. Okay, so this is system S of C. Okay, this is U1, this is U2, and this is Y2, and this is Y2. Okay, good. So same system, input 1, output 2, input 2, output 2. Okay, this should be 1, this should be 2. Okay, we perform a different experiment. This is S of C, where input is like this. U1 is multiplied with alpha, U2 is multiplied with beta. I sum all of them. This is plus, and I apply it to my system, and I observe my third output. If Y3 is equal to alpha times Y1 plus beta times Y2 for all alpha, beta, U1, and U2, my system is linear. Okay, so technically my system should satisfy both superposition and homogeneity properties. Then your system is linear, but your system is linear. It can still depend on time. Mathematically speaking, we can show it like this. So this is my system. This is my combined input here. Alpha U1 plus beta U2. If this is equal to alpha S of C U1 T plus beta S of C U1 U2 T, my continuous time system is linear. In discrete time, it's very similar. We show it like this. S of D U1 alpha plus U2 beta. This is N should be equal to alpha S of D U1 N plus beta S of D U2 N. Okay. If it is true, this equality for all alpha, beta, U1, U2, and N, your system is linear. Okay, good. Now let's talk about time invariance. Okay, so what is time invariance? Let's assume that we have a system and we apply a different kind of inputs. Okay, this is my input. Okay, so it's an output input. Let's make it simpler. Okay, let's assume that my input is step. Okay, and for the step input, let's assume that I obtain this output. Whoop. Okay. So what I do is, instead of applying the step at equal to 0, I will shift it with 5 seconds, for example. Okay. So now this is my shifted input. Okay. So if response doesn't change, or if the response is the shifted version of the original input, if it is like this, okay, then, and this is technically t, this is equal to t, my system is time invariant. Technically, its properties, its behavior doesn't depend on time. Mathematically speaking, in order to kind of show time invariance, we define a shifting operator, and shifting operator is this. Sigma t is equal to u of t minus t. Let's, okay, sorry, this is a system. Okay, so, and let's change the color. Sigma t u t is equal to u t minus t. We have also shift operator in discrete time. Sigma k u n is equal to u n minus k. Okay, so this shifting operator is also a system, and it's a very special and important system. Okay, so your system is time invariant Okay. If and only if it satisfies this following condition. SC sigma T U T. Okay. So here what I do is I have input. I first shift my input and then I feed this output of the shifting operator to my system and observe output. If this is equal to sigma T Y of T, where SC U of T is equal to Y of T, okay, then my system is time invariant. Technically, this is exactly my intuitive experiment here. So if you supply your input to the system, observe the output and shift it. Okay, this is what you do here. And if you do the shifting first and look at the output, if these two systems are same, two outputs are same, your system is time invariant. I technically change the order of the operations. Technically, orders of the system should be commutative. Okay, if you change a shifting operator in the system, you should always observe the same output for your system to be time invariant. And this property and the definition is same for discrete time and continuous time. Okay, so we are done with the shifting operator. And now let's talk about memory. Okay, memory. Okay, so we have a memoryless system, memoryless, and we have systems with memory. Okay, so memory system, let's say with memoryless, which is easy definition. If yt is simply a function of u of t, then your system is memoryless. Okay, it means that y of t depends on u of t only at time t. Okay, and now this becomes a system, but it's a special system. The system doesn't have memory. Your output doesn't depend on your past inputs or future inputs. Okay, just instantaneously you look at the input and you compute the output. It can be linear or non-linear, but it is memoryless. The good thing about memoryless systems, if your system is memoryless, it is by definition automatically time invariant. But we know that the inverse is not correct. Okay, your system can be time invariant, but it can have a memory, of course. But if it's memoryless, it is automatically directly time invariant. Okay, good. Okay, I don't do that. This is like this. Okay, good. Very simple. Okay, after we talk about memoryless, there's another property which is not very important for this course. This is causality. Causality. Okay, so what is causality? Okay, so let's talk about this. So I have input. Let's say input is look like this. This is my input. Okay, and I want to compute my output here. Let's say capital T. If my output is a function of inputs here, then my system is causal. If my output at any time depends on any featured data, such as here, then my system is non-causal. Okay, its idea is very simple. Your output should depend on only your feature inputs, past inputs. If anything depends on the feature, it's non-causal. Okay, so in this course, our goal is designing controls for real systems, which live in real domain, of course, physical systems. We will only cover causal systems and causal signals. Okay, so it's a good feature. But in signal applications, for example, image processing or other kind of things, your time may not be real time. It can be index of a picture, for example, in image processing or something else. You may design non-causal filters or you may deal with non-causal systems. But this course specifically only deals with causal systems. Okay, so how we can show causality using mathematics? It's also very easy. It's not very easy, but it's very nice. Okay, so in this case, we define a truncation operator. P of t, u, t is equal to u of t for t is less than or equal to t, 0 otherwise. Okay, so it's a truncation operator. So what we do is very simple. Let's show it here. Okay, so let's assume that this is my signal. And let's assume that my capital T is here. If I apply my truncation operator, it will be like this. Okay, good. So your system is causal if and only if PT S, let's say it can be discrete or continuous system, it doesn't matter. U, let's say discrete, should be equal to PT S PT U of N. Okay, so what does it mean? It's my input. I feed it to my system and I truncate it. In the other case, I truncate it, I apply my system and I truncate it. If these are equal, your system is causal. And this is if and only if statement. Okay, so let's assume that this is my input and this is my output. Okay, it's something like this. Okay, so in the other case, no, it's not okay. So let's show a more concrete example. Okay, and my system is an integrator. Okay, we know the integrators calls, right? Okay, so it is clear. So let's assume that my input is simply unit step. Okay, change this. This is my input. Okay, in the first case, what I do is I look at the output, change the color. Output like this, and I truncate. Okay. Okay, no, sorry. Okay, so this is the actual output. Cancel like this and change the color. If I truncate, let's say here, so this is my output. Okay, this is equal to truncated input of t. Okay, so let's do the other experiment. First, truncate my input. Let's use the same color. Okay, using here. This is here. This is my truncate input. Then look at the output. Okay, so let's go like this. Now it's 0, it's like this. Now this doesn't equal to this, right? Okay, but what we need to do is we need to apply a truncation operation again. Let's change the color. Now this is truncate, it's like this. As you can see, this red signal is equal to this weird orange signal. And since we already know that integrators causal, kind of graph to show in this example that it's causal. But of course, we need to do this for all possible t values. It's kind of easy to show that the system is non-causal because one example is tough. It's kind of harder to show that your system is causal. Okay, good. So there's one more system parameter that you haven't covered in signals and system course. So far, everything is exactly the same. And everything is we already covered. Only notation can be a little bit different, but this property is new and it's important in control systems, and it is finite or infinite dimensionality. Finite or infinite dimensionality. Okay, so before going to this, let's remember memoryless and memory systems with memory. Okay, in memoryless systems, technically, your system acts instantaneously. It doesn't need to store or know anything from the past or the future. Let's stick to the causal systems. Okay, memoryless systems, memoryless systems technically requires 0 amount of memory, and I will talk about memory later. So memoryless systems are automatically finite dimensional because its dimension is 0. Okay, because y of t is simply a function of u of t. Okay, if it's a linear time invariant system, y of t is simply equal to, let's say, 5 times u of t or something like that. Okay, good. Okay, so we know that systems with a memory. So what is infinite dimensional system? Okay, so what is infinite dimensional system? So before going to the definition, and definition is very simple. Okay, so the idea is this. So I have an experiment, and let's assume that my input is causal, my system is causal, and this is my input. This is u of t. Okay, and this is my time instant. Okay, this is my u of t. Okay, and u of t is equal to this, right? So until capital T, it has a value. Other than that, it's 0. And I want to compute my output. Okay. And again, specific, let's assume that, okay, my output is like this. Okay, until this time. Okay, very good. This is my y of t. Now I really wonder what happens after this instant. Okay, I want to compute y of t for t is greater than capital T. I know my input, it's a signal, until t. I want to compute my output. But what I don't want to do is, I want to use minimum amount of information to predict y of t here. Okay, so what I need to do? Okay, so if you need to compute y of t with finite amount of information, then your system is finite dimensional. But if you need infinite amount of knowledge, then your system is infinite dimensional. So what is infinite dimensional? For example, if you need to know all of the inputs, because we know that the time is continuous in continuous time, okay? So if you need to know all of the values here, everything to compute the output, it is infinite dimensional. Or, for example, let's assume that if you need to know all of the data here, your system is infinite dimensional. But somehow, if you can summarize all of this with a couple of initial conditions, let's say, okay, this is, if you know y0, it's enough. Or if you know y0 and y prime 0, it's enough. Okay, you can compute output. Your system is finite dimensional. Okay, so how you can check it? It's easy. Okay, so for a system, if you can write your system using an ordinary differential equation with finite number of derivatives, or if you can write the system in state space form with finite number of states, your system is finite dimensional. Okay, so you can think that, okay, this is easy. So if I have an ODE, it's finite dimensional. If I have a state space, it's finite dimensional. You can ask that, so this doesn't mean that all of the systems are finite dimensional. It's not true. There's one very simple and important system, for example, it is infinite dimensional. Okay, it is this. If y of t is equal to u t minus, let's say, t or 5, okay, what is this? It's a time shift operator in continuous domain. Okay, this system is infinite dimensional. Why? It's very simple. Let's assume that this is my input, okay, and this is 10. And let's assume that my capital T is equal to 5. And I want to predict my output here. So what I need to know? Okay, so if I know the values such as like 8 and 7, is it enough? No. I need to know all of the inputs from 5 to 10, all of this data. And we know that there's infinite amount of data here. I need to know all of them such that I can compute the output. This is a simply very nice infinite dimensional system. Time delay operator is an infinite dimensional system. Okay, so if you can write your system in an ODE form, state space form, or transfer function form using a partial fraction, technically a ratio of two polynomials, then it means that you can define your system using finite number of memory elements, such as RLC circuits. The dimension is technically defined by the number of capacitors and inductors. They are memory elements. because they capture the information in the past in an optimal manner such that you don't need to use any more computational details. Okay, so infinite dimensional systems are common in continuous domain, but they're not very common in discrete domain. So it's one of the good things about discrete time systems is because, for example, time shift operator is infinite dimensional in continuous domain, but if yn is equal to u k minus or n minus k, if k is finite, your system is still finite dimensional because you only need, for example, k number of past inputs. Or in a differential equation, only thing that you need to know here is, if it's like fifth order, you need to know 5 number of initial conditions to predict the output. For example, in the circuit examples that you solved in circuit courses, what you do is, in order to deal with switches, you look at the switching instant, you look at initial conditions of capacitors and inductors, and then, based on input or other kind of details, you can predict the output. But for some systems, you still need to store infinite amount of information from the past. Okay, so these are infinite dimensional systems. Okay, let's solve some quick examples, but you will solve many examples in the mini project, and then we can finish this course. Okay, so let's start with something simple. Okay, u of t is equal to tau of t, it's torque, and y of t is equal to theta of t. Okay, this is a simple pendulum. Okay, this is theta, this is torque. So is this system is linear? Of course not, because why it's linear? First of all, so you can apply torque. Okay, it will go somewhere else. But as you can see, output is limited, right? Okay, because theta in element of minus pi to pi. So this is like this. Okay. So if let's say you apply 1 Newton, you look at output. If you multiply with like 1000, your output of course will not be 1000 because there's a saturation at the output. We also know that because of the mass, because of the gravity, it acts like a nonlinear spring, and it's a nonlinear system. Okay, so it's nonlinear. However, it's time invariant because it's a physical system. It doesn't depend on time. If you wait 5 seconds, if you apply your input, it will be the same thing. It's causal, okay, because it simply doesn't depend on the feature. The system has a memory. It's important, memory. It's not a memoryless system, okay? The system has a memory because you need initial conditions to compute the output. You need information. And it's finite dimensional because if you write this in ODE form, second order ODE is enough to capture all of the details. And it means that in order to capture the future behavior, 2 initial conditions are enough. And in state space form, you need only 2 states to represent the system. Okay, so for example, in this system, it's nonlinear, it's time invariant, it's causal, it's memoryless, no, it has a memory, and it is finite dimensional. Okay, so there are other examples in your lecture notes. You can look at them. And in the mini project, you will solve many examples. And it's a kind of nice to solve different examples to refresh your knowledge from signals and systems course. Thanks for listening.